Hello, welcome back to CS460. So last time we stopped here, introduced a way to analyze the running time of the insertion sort method, insertion sort algorithm. Okay, so basically we would assume that each line of code uh, if that line of code is executed once, then we assume that it costs constant amount of time. And the second step of analysis is to determine or to estimate how many the execution number, the number of execution times. Okay, so it's basically this quantity that we need to decide in order to compute the final running time of the algorithm. There are several tricky points here. First one, when we say the number of times or how many times each line of code is executed, there will be a difference between this first line of the for loop versus the inside of the for loop, the inner bodies of the for loop. Okay, so let's look at the range of this for loop. Right, we basically pay attention to the starting number and the ending number. So assume the a dot length equals n. So if we focus on the loop counter j, the j will start with 2, and then the next one will be 3 and 4, right? And the last execution of the for loop body, the counter will be n. Okay, so for loop counters between for loop counters from 2 for j equals for j from 2, 3, 4 to n, which includes n minus 1 integer numbers. So this quantity, the n minus 1, is the quantity, is the number of executions for all lines of code within the for loop. Okay, so the difference from the first line of code, which is the for loop statements, right? So what's implicitly included in this for loop statement is that after the last iteration, in which n equals n is executed, the j will increment once more for one additional time. So that's j equals n plus 1, and it breaks the condition for the for loop. So that's why the number of times here is n, which is one more time than all of those internal lines of the for loop. And this is a universal property that applies to all kinds of loop structures. So that's why when we go to the next page, when we see the while loop, okay, you can see that for the j's while loop, the while loop statement takes t subscript j times, okay? And for all these two lines within inside the while loop, they will be executed one less time than the t of j, okay? So this type of formal analysis in which you write down all those constant costs, all those number of times listed here, and then you compute the total running time by summing up all the products is very useful way, especially you have relatively complex code structures. For example, like there are multiple layers of loops. Okay, it'll be a really useful technique. Okay, but later on, as we get more and more familiar with different types of algorithms, with different types of loop structures, it'll become easier for us to immediately estimate the running time without listing all those costs and the number of executions. All right, so let me enter the next page. Last time, yeah, this time we have, for this slide, we have already covered it, right? So it's a simplified case-by-case analysis. For here, we are analyzing the best case. A best case for a sorting algorithm occurs when all the inputs elements are already sorted. Okay. So I see a question. What is summation of the while loop? Why is it from? No, it's not from 2 to j minus 1, but it's from 2 to n, because that's the range defined by the for loop, right? 2 to n. If you count how many numbers are there between 2 and n, you'll find it's actually 2 minus 1. Okay, so it's not really j from 2 to n minus 1, but it's from j to n. Like, imagine n equals 6, then 2, 3, 2, 3, 4, 2, 3, 4, 5, 6. That's 5 numbers, right? All right, so yeah, so for the best case, the input array is already sorted, which means each time you take one card from the pile on the table, and you find you don't need to move it forward. You don't need to compare it with all the cards in your hand. You just directly insert it. So the while loop basically doesn't execute. Okay, in this case, there's no need to execute the body of the while loop. Okay, and we only need to execute the while condition, the while statement for once, which means the TJ would be only 1. Okay, for all the J's. So when we substitute TJ equals 1 into the equations from previous slide, we will see that the total running time would be some constant times n minus some constant. So it's a typical linear function. Right. That's the best case. And of course, there will be a worst case. And the worst case for a sorting problem occurs when the input sequence is in the totally reversely sorted order. Okay. So that means when you take out a card from the table, you have to compare with all the elements before. Okay, we need to compare the key with all the elements that is before it, right? Which is from 1 to j minus 1. So we can assume that the tj equals j. Okay, and we after substituting it into the formula, we find that the summation of j, right, is the sum of a arithmetic series. Okay, and it's in nature a quadratic function. And after we clean all those coefficients, it becomes a general form like something times n squared plus something times n plus c. Okay. Right, so we can see that worst case and the best case, they dramatically differs from each other. All right, next, let me start playing the slides and reshare the screen again. we're gonna see how the average case looks like. Actually, it's quite easy to get when we already know the worst case. Okay. And usually speaking, the average case is something we need to approximate because we don't have information about what kind of input we are expecting. The input can be very random inputs sequences or inputs arrays. Okay, right. And for typical algorithm analysis, focusing on worst case is sufficient. Yeah, because we want to get prepared for the worst scenario, for the worst case, right? Because it gives an upper bound for any type of input, right? When we know the worst case improvements, or when we know the worst case performance, we will have a sense of how fast or how quick an input an algorithm can run. Okay? And worst case occurs fairly often. Okay? Like searching a database with information when the key information is absent. This is a very often case. All right. And for insertion sorts particularly, okay, for insertion sort particularly, the average case is more or less the same as the worst case. Okay. So let's suppose we randomly choose n numbers for insertion sort. And let's consider the question. Because when we in the worst case, when the input is a reverse order, so each time we take a card, it needs to be compared with all the cards before it. Okay, so then how many times it would be likely? How many times on average it's likely to be when it's kind of a average number, right? So we can assume that when on average, half of the numbers before it are less than the target, less than the key, while the other half are greater. That is a pretty reasonable guess, right? We can guess that when we take number, it's almost the mean values of the sample. Okay, so it's reasonable to expect that on average, we can have TJ equals half of the J, which stands for half of the elements that's before the key. Okay, so this is a reasonable number that we use to analyze the average running time. So let's substitute this term into the equation, and we can basically have the same function, because the summation of J, right, when you compare it with the summation of half of J, right, when we compute the right term, we can take this 1/2 outside, right? So regardless of the constant coefficient here, which is 1 on the left and the 1/2 on the right, the inside here is still the summation of J, which is still a quadratic function. Okay, so we can say that the average time for the insert and sort is almost at the same level as the worst case scenario. All right, so that leads to the next concepts of the order of growth. Okay, we can use this mathematical notation or a way to abstract to help simplify our analysis. Okay, so this principle is that we can ignore the actual numbers. We can ignore the actual cost, but use constants instead, okay? And we can use abstract form like this, T of n equals A times n squared, B times n plus C. And we can do a further simplifying abstraction, which is that we only consider the highest order of the function, okay? We only consider the leading term. In this function, A times n squared plus b times n plus c, we can ignore the lower order terms, because relatively speaking, when you compare the quadratic function with the linear function, the quadratic one will grow much faster than the other one. So for large values, for large n as inputs, the difference, the b times n plus c would be irrelevant when you compare to the a times n squared. Okay, and we can also ignore the leading terms coefficient. In this case, it's the constant a. Okay, so we can rewrite the worst case running time as big theta of n squared. Okay, it's just it's the first time we introduce big theta, and we will introduce it more systematically in our next lecture. But for this time, we can just take it as a convention to write the order of growth. Okay, it basically tells that the function grows as fast as the function n squared. Okay. And the order of functions is the determining factor for how fast an algorithm is. Okay, if the different algorithm that runs for big theta of n cubed, that amount of time, for that running time, it must be a much slower function than this big theta of n squared algorithm. Okay. We can know the difference from a glance of the order of the functions, of the growth functions. Okay. All right. So for insertion sort, we're pretty much done, and it's useful if we remember that the worst case or the average case running time for insertion sorts, it is big theta of n squared. Okay, so do you still remember the best case if we want to use big theta to describe the running time of insertion sort for the best case? Someone can give the answer. Yes, that's correct. The best case is a linear function, right? We use a times n plus c. So we can simply ignore the constant terms in the lower order and put an n here. So for the difference between big theta and big O, that's another topic which we will cover in our next lecture. Mathematically speaking, we have to strictly define the differences between big O and big theta using formal languages. Okay, but for short, we can say to claim that the big theta is a tighter bound. Okay, when we say big theta, we have more confidence and we have more information in it. But for big O, it's more about the upper bound. Okay, for big theta, it's kind of both the upper bound and the lower bound. Okay, so it's a more informative or more accurate description as compared to big O. And big O is looser, is a much more loose description. More of a range. Big O is more of a range, I guess. Yeah. Okay, let me clear these drawings. And today our next goal is to go through the divide and conquer approach, which introduced the second the second sort algorithm, which is merge sort. Okay, so I recommend you to go through the textbook after the lecture today. And similarly, we're gonna have a pseudocode implementation of the merge sort algorithm, and we will also have the running time for the algorithm analyzed. Okay. All right. It's an alternative approach to sorting problems. Okay. The name of it is called divide and conquer. Okay. And we will have a special chapter for this family of algorithms. But today, let's just have a quick review, have a quick view of this type of method. So for this type of method, algorithm, as the name indicates, we need to take the original problem and breaks it into several subproblems, okay? And each subproblem is similar to the original problem, but only different in the smaller size, okay? So that means we can solve the subproblems recursively, okay? And then combine the solutions to create a solution to the original big problem, okay? All right, so there will be several steps for defining a divide and conquer algorithm. All right, so here the recursive term means that in order to solve the problem, we can call the algorithms recursively for one or multiple times. Okay, let's look at the 3 steps of a typical divide and conquer approach, which is first divide, right? We divide the problem into smaller ones, and conquer, solve each subproblem recursively, okay? Which may cause further division, okay? The recursive call is critical here. And if the size of the subproblem is small enough, then it means that we hit the recursive boundary. We hit the boundary of the recursion. There's no way to further divide the problems. So in that case, we need to solve the problem in a straightforward manner. And usually when we hit the smallest, when we meet the smallest subproblem, it will be a trivial problem. It will be a really simple problem. Okay, divide, conquer, and then the last step is to combine. Okay, now we simply collect all the solutions from all the subproblems and then piece them together into the original solution to the original problem. Okay, and merge sort is one of such a divide and conquer algorithm for sorting problems. And the advantage of the merge sorts is that it has much less running time than the insert and sort in the worst case. Okay. Okay. Let's look at the basic idea of merge sorts. So first, the divide step, we will divide the inputs for divide and conquer approach. Does it have to use recursion? I don't think so. So there will be non-recursive implementations. Okay, but a recursive style is easier to understand conceptually. Okay, although there will be more implementation details that we need to pay attention to. Okay, so let's look at the divide step. Okay, when we have n elements in our inputs, it's just straightforward to cut the sequence into 2 halves, right? And we have each subsequence that contain n over 2 elements in each, right? And the conquer step is to sort the 2 subsequences recursively using the merge sort algorithm that we are defining. Okay, and the last step is to merge the 2 sorted subsequences to produce the sorted answer. Okay, so this merge step is critical. Okay, because it's not an easy job. When we have 2 sorted sequences and we want to merge them, we have to figure out which one comes to the first, which one comes to the next, right? So this is the procedure that takes efforts. Okay, remember there, just imagine there are two piles of cards on your two hands, right? And you are sure that each pile is already sorted. And how do you merge them together so that the final result is also sorted? So this is a question that we need to take some time to look into. Okay. So here we'll introduce a recursive solution, and the recursion will reach the bottom, which is the base case or the boundary case when we have a sequence that has length 1. Okay, so for a sequence of length 1, which is just one number, right, and there's no work, actually no work to be done, right? We don't need to sort a sequence of 1. Okay, so as we can see, the merging steps is the critical step. Okay, all right, so let's directly look at the code. We will, in order to define a merge sort, we will first define some auxiliary or helper procedure called merge. Okay, it takes several arguments as inputs, and on next page we will explain the roles of these arguments. Okay, so A is an input array. Okay, and those P, Q, R's are the integers indices. Okay, the PQRs are the indices, and they satisfy that the Q is in the middle. The Q is between P and R. Okay, so the P is the kind of the left end, and R is the right end, and the Q is somewhere in between. Okay, so and we have another assumption, which is that the sub-arrays, which is the first one from P to Q, and the second one from Q plus 1 to R, they are already sorted order, right? So that's our assumption, right? We need to assume that the two subsequences are already sorted before we start merging them. So I see the question from Steven. So it is when we implement the merge, we need to guarantee that the final array will be sorted. Otherwise, we're not accomplishing the algorithm. Okay, so like if given two already sorted input sequences and we merge them, but the merge results is not a sorted algorithm, then that's a failure. That breaks the principle. We have to make sure the merge always return a sorted sequence. Yeah. Okay. So our goal is to merge the two subsequences. The first one is from P to Q. The second one is from Q plus 1 to R. And we need to merge them to form a single sorted subarray. Okay. And to replace the current subarray. All right, let's dive into the code here. All right. So yeah, so there's still some analogy on this slide. I like using the playing cards as an example, right? Just imagine in your head that there are two piles of cards in front of you, okay? And each pile of card is already sorted, and we know that the smallest card is on the top and the biggest one is at the bottom, okay? And we need to merge the two piles into a single sorted output pile, okay? So what we need to do is actually a straightforward strategy. We can choose the smaller of the two cards on top of the two piles, right? We can take two cards and take a look of the two cards and place whichever the smaller one from that two, and place it onto the output pile, right? And for the bigger one, we just leave it in its original pile, okay? And we'll repeat this step until one input pile is empty, right? And then we will append the remaining pile, the other pile, to the output pile, right? So that is a basic strategy we will take. All right, so one technical detail is that each basic comparison takes constant time, right? It's a simple comparison. We just take a look at two cards and tell which one is bigger. All right. So yeah, so first of all, I put the conclusions here, because we can perform at most n basic steps, and in one basic step it's just a comparison. So the merge is a linear, or will take linear amount of running time. Okay, it's not a super expensive algorithm, right? So like in the simplest case is that you have two piles that are basically the same size, right? And whenever you made a comparison, there is one card less, right? So it basically needs to make basically n times of comparison. And finally, you will get a merged sequence that is 2 times n length in length. Okay. Let's see the code here, right? So that's the code given by our textbook. Okay. So the textbook here it's introduced in an interesting way to save some amount of calculation, amount of execution, by introducing the special type of characters like these infinity characters. We will see the functions of it. Okay, but just look at the inputs. Yeah, let's draw the input here. Assume that input is an array, right? That's from index P to index R. And we assume the two have already sorted, right? So the first line of code, it computes the length of the left subarray, which is from P to Q, right? We know that Q is bigger than P, so Q minus P plus 1 will be the number of elements in this subarray. Okay, and for the right half, it will be R minus Q plus 1, and then plus 1, which will be R minus Q. Okay, so that is the length of the two halves. And on the third line, we allocate some new spaces. Okay, we create a new array, okay, to store two new arrays to store the two subarrays. Okay, and for the first two for loops, they are actually simple operations that copies the original elements from A to the two newly created arrays. Okay, so it's simply a copy from the left subsequence to L and the right subsequence to R. Okay, so it's some extra memory space we need to allocate. All right, so from line 1 to line 9 here, it's a preparation step. And for 8 and 9, we append some special characters called sentinel value, which is infinity. Okay, which means this infinity value is larger than any other values. Okay, so this is just for the convenience of our next step comparison. Okay. All right, the real merge occurs next. Okay, the real merge procedures occurs from line 10 to 17. Okay, and it's basically a for loop. Okay, and we prepare two counters, which is I and J. Okay, And these two counters are used for the left and right sub-arrays respectively, okay? And there's a third counter, which is K, that ranges from this start of the array to the end of the array, okay? K is a third counter that we use to slide from the head of the array to the end of the array, okay? Because we want to make the rearrangements of all the elements, okay? So what it does for within the body of the for loop is an if and else condition, right? We are making a comparison before we are making a comparison between the two top numbers or top elements within L and R, right? We take the top elements from L, which is Li, and the top elements from R, which is Rj. And if the left one is smaller, then we will copy the smaller one to the current position of A, okay? And then we increment the counter for the left array, right? By incrementing I plus 1, right? Which moves I 1 to the right. If else, then it means the right element is smaller, then we will copy this right element to the current position in A, and then increment to the right counter. Okay, it's like two sliding windows. Okay, so that is the implements of the merge. Okay, and the Sentinel value would allow us to writing less code in checking which empty is empty or not. Okay, so it's a common strategy used. Okay, and this for loop, if we look at the range, it actually runs R minus P plus 1 basic steps to for the comparison. All right, so that's the code, and let's look at a simple example here, which will make it much clearer to understand the code. Okay, let's assume our input to the merge function looks like this. Okay, our P is here, P is 9, Q is 12, R is 16. Okay, so all those values in it, we can see that the left is already sorted and the right is already sorted. Okay, and so our task is to merge them. Yeah, so we write two new arrays and then rewrite the original one. Yes, so the original one is rewritten. Yeah, so it's basically the elements is sorted in place, but with the help of 2 extra memory space. Yeah. All right, let's look at an example here. Okay, so that's the first iteration, right? Because we compare the Li and Rj and found that Rj is smaller. So we copied the Rj to AK, which is here, right? And we increment j by 1, which means we will remove the R1, right? And our next step, when we compare Li and Rj, we find that the if condition is satisfied, so we will copy the Ri to A and then move I 1 grid to the left. Okay, so all the basic steps will follow in the next page here. Okay, next will also be Rj because 2 is smaller than 4, and next 3, right, Rj, and next we went to Li, next Li2, okay, next will be Rj. All right, so when we hit Rj, when Rj hits the infinity sentiment the sentinel character here, sentinel value here, everything left in the L, in the left range, in the left sub array will be directly copied to the remaining parts of the sub array here, K. Okay, but it's also it still takes some time depending on how many elements are left in L, right? All right, so that's a complete example of running through. So the sentinel value, the mechanism provided by the sentiments value is that it's a greater the infinity is always greater than any other values. Okay, when the RJ hits the infinity code, hits the infinity, yeah, so it's actually it's an actual infinity, but in different programming languages handled differently. So in Python, there is a way that we can define infinity with the math package or the numpy package. Okay, so I think we will. I have the programming assignment ready for the first assignments, and you will see that how it is defined in Python. Yeah. All right, let's look at the next. So at this point, after the for loop executed, the for loop terminated, everything in the sub-array A from 9 to 16 is in sorted order. Okay, as we all can see, now it's in a perfectly sorted order. Right, we can rerun this process later on paper or in our mind after the lecture is done. So it's basically a simulation of the card playing game, right? You compare two cards, take the smaller, put it into a into the pile, and so on. All right. So for the loop invariant parts, I'm going to skip it because it's an optional contents for you to check the correctness of the algorithm, similar to the insertion sorts. I'm going to skip it. Okay. Yeah, let's directly go to the running time analysis for the merge procedure. Okay, so as we have already given the answer, it's big theta of n, because the for loop runs from P to R, and R minus P plus N is the total number of elements being merged. Okay. If we look at all those lines, we can basically ignore those lines that have been only that has only been executed for once or for a constant amount of time. For example, from line 1 to 3 and the 8 to 11, they all take constant time. And the for loop from 4 to 7, right? There are two for loops, and they takes big theta of n1 plus n2, because that is the range for each for loop, right? So in total, they take big theta of n. And for the last for loop, it takes also big theta of n times. All right, so there are two parts in the algorithm that takes a linear amount of running time. So summing those all together, we can have a big theta of n times, which is a pretty straightforward solution for the running time analysis. Okay, so here we are just done with the final step, right? In the divide and conquer approach, we first divide and then we conquer and then we combine, right? So the merge procedure is for the combining step, right? given two sub-arrays that are already sorted, then we can merge them within linear running time. So now let's deal with the previous two steps, which is to divide and conquer, okay? All right, so we're gonna use the merge procedure we just defined in the final merge sort procedure. Okay. This is how the final merge sort procedure looks like. Okay. All right, so it takes the array A and the starting index P and the ending index R as an example. So it will first check whether the index P is strictly smaller than R. Okay, if so, it means there are more than one element, right? If P equals R, then it basically means it's only one element. But you know, for sorting in one element array, we don't basically need to do nothing, right? So the body of the code for the merge sort code, it ignores cases where there's only one element. And the code will only be executed for elements that's greater than, that has more than, that has at least two elements, okay? So the first line of the code will divide the elements into two sub-arrays, right? It will compute the midpoints, right? Midpoints between P and R. So these brackets, half brackets, is for computing the floors of a floating number, right? So Q is the midpoint between Q and R, between P and R, okay? So now we have divided into two sub-arrays, which is from P to Q, and the second half is from Q plus 1 to R, all right? So this third line and the fourth line is where the recursive call occurs, right? It's the calling of the function itself, right? We are defining the function merge sort, and within definition, we are calling the function itself, right? There are two recursive calls, but with different indices. The first call is called on P to Q, and the second is on P plus 1, Q plus 1 to R. Okay. So the purpose of these two recursive calls is to sort the two halves respectively. And after these two are already sorted, we will call the merge procedure, which is what we just defined in the previous step, right? And then we're done with the merge sort. Okay, so that is how the code is written in the merge sorts, right? And in order to sort an entire sequence, for example, from A1 to AN, we can simply call it with a merge sort on A with 1 as the starting index and A.length as the last index. Okay. All right. So let's look at some let's step into the calling procedures, because merge sort, because the recursive call, it's a little bit hard to keep track of at the beginning, but we can use a simple example to see how the recursive calls occurs. Okay, so let's look at a input that is basically in random order. Okay, we have 5, 2, 4, 7, 1, 3, 2, 6 in our input array, 8 numbers. Okay, and according to the algorithm, we should call the merge sorts on the array A with starting index 1 and ending index 8. Okay, the first code is to compute the midpoint, which is the number 4, right? So this is the Q, right? The Q is 4. And then we call the merge sort again on the left, right? And on the right. And then we will merge it, okay? So this first subcall of the merge sort, right? Let's step into this subcall. Okay, so within this subcall of merge sort from 1 to 4, we have to compute another queue, right? That's within this sub-array. This new queue would be the midpoint between 1 and 4, which will be 2. So that is also our second queue here. Okay. Another merge sort will be called on the sub-array, which is this one from 5 to 2, right? And the second merge sort will be called onto this sub-array from 4 to 7. Okay. In this case, the sub-arrays, I see the question, the sub-arrays are the same size, but it's not necessarily so, because when you have 5 elements, right? So the floor operation will make the first one smaller, will make the first sub-array 2 elements, and then the second one only the first one 3 elements, and the second one 2 elements. Like that. Yeah, if the total size is an even number, then basically if the total size is a 2 to the power something, then it's a perfect split of the equal sizes. But that's that doesn't matter. It's okay if we have different sizes. Okay. All right. So we have another layer of subcalls of merge sorts. So we can keep dive into, for example, into this call. We can keep dive into this subcall. It's a merge sort on the first element to the second element, right? We will need to compute another midpoint, which is Q equals 1, right? And Q equals 1 means that our next merge sort call would be on A1 and 1. And second will be A2 and 2. Yeah, because Q is 1 here. Okay, that's our Q. And a merge sort on one element will basically do nothing, right? Right, because our code tell us that if the 2 indices are the same, then it will do nothing. Okay, so we will only execute this merge code. We will merge the sub-arrays from 1 to 2, and 1 is the midpoint. Okay, so this merge, after this merge is done, we will return to the upper level, right? And enter this level in the middle, which is a merge sort on from 3 to 4, right? And on the 3 to 4 merge sorts call, there will be a Q equals 3 computed. And similarly, these 2 merge sorts will do nothing because they have the same starting and the ending indices. And the final merge at the current layer will return to the upper layer, right? This merge will be conducted between the on the sub-array from 3 to 4 with 3 as the merge points. Okay, and we return to the upper layer, and the merge of the upper layer will return to the first layer. Okay. All right, let's go to the next page. Oh, yes, it's be right here. So the first merge procedure will execute it on the first sub-array, right? From 5 to 2, from these 2 elements. And the merge result will return a sorted sub-array from 2 and 5. The second merge will be 4 and 7, right? The third merge will be 1 to 3, and then 2 to 6. And the next layer would be the merge between these 2. And the result will be 2, 4, 5, 7. And it's a sorted order. The next merge will be between the left, which is 1, 3, and 2, 6, which results in 1, 2, 3, 6, right? And the last merge is on the top layer, right? Which will be the final results 1, 2, 2, 3, 4, 5, 6, 7, right? Which is in the correctly sorted order. Okay, so that's how merge sorts is visualized. I would strongly recommend you to go through the same example on the paper so that you can understand at which step the merge occurs, the merge procedure is called, and the merge occurs, merge results in the sorted sub-array. Okay, it will be much easier, it will be much clearer if you run it yourself on the paper. Right. So the next step is to analyze the running time of merge sort. So it's a bit tricky now because the merge sort is implemented in the recursive style. And the recursive style would contain the function itself, right? Let's look at the technique that we use. We can describe it actually using a technique called recurrence equation, okay? So which basically describes the overall running time on the problem of size n in terms of running time on smaller inputs. So it's actually is an equation that can be solved with mathematical tools. Okay. So let T of n be the running time for a problem of size n. So if the problem size is smaller enough, right, and the straightforward solution takes constant time. So in the case of merge sorts, if n is smaller than 1, then we will simply return the array, right? So that is the case for the merge sort. And if we divide the problem into A subproblems, and each subproblem is 1 over b the size of the original problem, then we can simply write the running time for the subproblem as a or a t of n over b time. Okay, and overall it takes a times t of n over b times. And in the case of merge sorts, both a and b are 2. So let's go to the next page to see a more specific form for merge sort. Okay. Yeah, next page. And also, when we analyze the running time, we need to suppose that we also need to consider the cost for the dividing and the combining, okay? Because these are all part of the algorithm. So in the final form of the running time of the recurrence, it'll be look like this. If it's the smallest problem, then it's a constant running time. In other cases, we have to consider the cost of dividing the problem, the cost of combining the solutions, and the recursive cost. Because there are A of such recursive calls, and each recursive call will take that size of the inputs. Okay, so this is a general case. And this form is actually solvable, and we will introduce a systematic way to solve such a problem in our next chapter for divide and conquer algorithms. But we will generally introduce it for today for the merge sort, right? So it's a bit simplified. We simply assume that original problem size is n the power of 2, right? So the dividing step is quite easy. It's just to compute the Q, right? Q is the midpoint of P and R. And the conquer step, because each subproblem is half the size of the original one, so the total is 2 times n divided by 2, right? So, and we already know that the merge procedure which is for the combining step. It takes linear running time. So altogether, we can write the recurrence equation into this form. 2 times T of n over 2 plus theta of n plus 1. That is for cases where there are more than one element. If there's only one element, then the running time would be constant. Okay, so that is for the recurrence equation. And we can further rewrite it by ignoring the constant, the lower order terms. Okay, let's have a further simplified version of it. We basically replace all the big thetas with actual constants, right? The big thetas and the big thetas here with actual linear functions and the actual constants. So it will be a concrete equation that we can try to solve now. Okay, so let's look at the solution provided by the textbook here. Our T of n, right? If we observe the part here, T of n equals 2 times T of n over 2 plus C of n, right? This is a summation. We decompose this summation into 3 parts, which is C of n. We write the C of n at the top node, and there are 2 T of n over 2. So we split this 2 times T of n over 2 into 2 branches. One is here, the left branch, and one is other on the right branch, right? So that is rewrites of the original form. And now what we can do is to further split the 2 nodes, left nodes and the right nodes. Okay, so by replacing the n over 2 into the original recurrence equation, right? If we replace the n with n over 2, then here it will become n over 4, right? And here it will be c times n over 2. So that's why we replace c times n over 2 here, and the left branch into n over 4 and the right into n over 4. And same for these 2 nodes here. And this actually split procedure can be carried on further, right? We can further split all those nodes until a point that we hit the smallest case, okay? Because you see our numbers within this T parenthesis becomes smaller and smaller, right? The next step would be n over 8, right? And n over 16, n over 32. But that doesn't infinitely goes down, because we will hit the boundary case where n becomes 1. So the leaf node would be C, right? So the leaf node at the bottom of the tree would be C. So anyway, we will have finally like a tree structure looks like this. Okay, and what we can do is to look at each layers, because remember, so this whole tree structure is the total running time of the merge sort, right? The way we get this tree structure is to split the term T of n. So if we can sum up all the elements within this tree, then we will get a solution to the T of n. Okay, so let's quickly observe the tree, and we can find something very interesting. The first layer, the root layer, right? It's C of n. And the next layer is 2 times C of n over 2, which is still C of n. The next layer is 4 times C of n times over 4, which is still C of n. And we can guess that for all the layers below, even for the leaf nodes, right? The leaf nodes is n smallest subproblems, and each problem takes C constant amount of time. So the last layer, the final layer, is also C of n. Okay? So all we need to know is how many layers are there in this tree, right? How many layers are there in this tree? So it is something we can estimate. Okay. So actually, the number of layers is the logarithm of n plus 1. Okay, so this is a property that we will come into across very frequently for future analysis. Okay, because for each level, for arbitrary level I, the number of nodes is this quantity. The number within the nodes, right? So for example, for level 1, let's call it level 1, right? The number in this node is c times n over 2. And the root node, let's call it number 0. So it's c times n over the 2 to the power of 0, which is 1, right? So that is something we can observe. And we know that when this number, when this value, c times n over 2 to the power of I, hits the constant c, then we will reach the lowest level, right? So when we eliminate c here, we will have this equation, and we can solve the I by taking the logarithm of n, right? So it means that when I reaches log of n, we will reach the lowest level. So altogether, we will have logarithm of n plus 1 layers, because we need to include these layers 0. Okay, so altogether, we have that many layers, and each layer has c times n. So the result will be c times n times logarithm of n plus c times n. Okay, and we can ignore the lower order term, and we know that the linear term is at lower order than the c times n times logarithm of n. So the total running time for the merge sort will be the big theta of n times logarithm of n. All right. And this is a function that we are happy with, because we will explain more in the chapter of order of functions. But now all we need to know is that this function grows slower than the quadratic function. Okay, in insertion sorts, the average running time is a quadratic function. But for merge sorts, the average time is big theta of n times logarithm of n. So merge sort runs faster. Okay. All right, so that's pretty much of the merge sorts and insertion sort as an introduction. And I see a question about the space complexity. That's something we can measure quickly, because it's also pretty obvious. If we look at how many memory space it costs, let's go to the code for merge sorts. Actually, we just need to notice that the merge, right? Each merge call, oops. Each merge call would allocate some new spaces, right? And the length of these two smaller space actually is the same as the length of the A. So we can say each merge operation costs linear time of extra memory space. But what would be the total memory space cost? Then we need to refer to the same recurrence equations. Okay. Yeah, although here we are only more interested in the running time instead of the memory space. And for the insertion sort, we already know that the insertion sort doesn't require extra memory space, so it would be pretty much constant memory space? Well, I would say if we consider the inputs as a cost for the memory space, then it's pretty much linear memory space cost. Yeah, but for the merge sort, we have to consider each level of memory cost, right? The merge, each step of merge will cost the linear amount of time. So this time there will be 2, and this time there will be 2, right? And the next, oops, let's quickly plot this. So this time will be 2, and this time will be 2. Here will be 4, and will be 4. And lastly, there will be 8. Okay, so it's quite a lot of memory memory costs. And it's also, if we observe the structure of all those number of memory spaces, it's kind of a similar value as the running time cost, because the first layer is 8, the second layer is also 8, right? And this layer is also 8, right? I would say something similar to n times logarithm of n. Okay. Right, so it's a typical trade-off between memory space and running time. All right, so that's pretty much for today, and I would encourage you to go through the the merge sorts parts on the textbook, and I will release the first programming assignments and the first question set as well. So all the question sets are paper-based, and it will be in a PDF file, and you can work on it on the paper and submit the scan. For the programming assignments, it'll be in the Jupyter Notebook, but I know I haven't covered the notebook tutorials as of yet. Maybe later I can I can post the link to the introduction of Python and Jupyter Notebook from my other course this semester, which is CS549. And I think it's sufficient to cover everything we need to know about Jupyter Notebooks for this course. Okay, so do you have other questions today? Yeah, there are cases we should care more about memory cost. So I've heard something about merge sorts because when we have too many data to merge, it will actually cost a lot of memory space. And when we do need to handle large amount of sort large number of data, large number of numbers, we usually would rely on some more memory space efficient algorithms, maybe like heap sort or quick sort or other stuff. But also it's cautious. We need to be cautious when we implement recursive algorithms, because whenever we have a recursive call, we will push our function head to the stack of the computer, and our stack will soon get overloaded if the recursive depth is too much. Yeah. Usually nowadays, when computer memories become more accessible, I would say running time will be the primary concern. I will release quizzes later after I have this course content uploaded on Canvas. Yeah, there will be quiz questions today. The class will be in person after February 7th. Yeah. So the week, yeah. So for February the 8th is a Tuesday. We will be in school. We'll be on campus.
Wait, I thought the first day of on campus is February 7th.
Yeah, that's first day. But our course, our class on that in that week is Tuesday and Thursday. Which is February the 8th.
Ah, yes.
Okay, yeah, I noticed that.
Thank you.
Thank you. All right. Okay. Everybody have a nice weekend.